This is the 9th video in a series devoted to differential equations. And we just wrapped up our initial discussion on first order differential equations by looking at some applications. And now we're going to look at second order linear differential equations. And so these equations will have a most general form that's like this. We have functions p0, p1, p2, and f, and then the following combination of these with y double prime, y prime, and y. So I'd like to recall that by a linear differential equation, I mean that it's linear in terms of the dependent variable and its derivatives. So here that would be in terms of y prime, and y double prime. It need not be linear in terms of the independent variable x. So that's why this is the most general form of a second order linear differential equation. But what we'll generally do here is multiply by 1 over p0 of x, and then we'll get the following differential equation that's a little bit simpler. So notice that this may not always be available. We may end up getting some zeros in the denominator, but we'll talk about that when we get to it. So this is also like kind of a nicer form of a general second order linear differential equation. We have y double prime plus p of x y prime plus q of x times y equals f of x, where f of x is known as the forcing function. And a really important special case here is the case when f is identically zero, so it's the zero function. And in that case, we say that we have a homogeneous second order linear differential equation. So the equation is homogeneous. Now, if f is not identically zero, which means it's non-zero for some value of x, then we say that this is a non-homogeneous differential equation. Okay, so this video we're going to be proving some results involving these differential equations. We're not really going to look at solution strategies, although we will look at solutions to some particular differential equations. So the first result that we'll prove is that if we take the homogeneous second order linear differential equation, y double prime plus p of x y prime plus q of x times y equals 0, then its solution set forms a vector space over the real numbers. Obviously, we're working with real valued functions here, so this would be over the real numbers. And I guess this is kind of a sketch of a proof, although if you look at the axioms for a vector space, you'll see that this is indeed sufficient. So what we'll do is we'll take two solutions. So we'll take y1 and y2, and we'll say that these are solutions to our differential equation. So by our differential equation, I'll just say that differential equation up there. And then what we'll do is show that any linear combination of these two solutions is indeed a solution. Okay, so now let's consider, like I said, any linear combination. So I'll call that linear combination y. That'll be c1 y1 plus c2 y2, where c1 and c2 are real numbers. Great. Now let's plug this y into our differential equation and see what happens. So we have y prime, double prime plus p of x times y prime plus q of x times y equals, well, we have to take the second derivative of y and the first derivative of y, but since c1 and c2 are constants and we've got a sum of those things, we can use the linearity of the derivative. This will give us c1 y1 double prime plus c2 y2 double prime from taking the second derivative plus p of x times c1 y1 prime c2 y2 prime, and then finally plus q of x times c1 y1 plus c2 y2. Great. But now we can put our like terms together. So here that'll be c1, and then we'll have a grouping of y1 double prime plus p of x times y1 prime plus q of x times y1. And let's color code where those came from. That came from this underline right here, this underline right here, and this underline right here. So let's maybe underline this whole thing in orange. Keeping in mind that we distribute that p of x and q of x through. And then we'll have something similar with 2 as the subscript. So this is going to be c2, and then we'll have y2 double prime plus p of x times y2 prime plus q of x times y2. So let's color code that as well, maybe in purple. So these purple underlined terms turn into that thing that I've underlined in purple. But now, given that y1 and y2 are solutions to our differential equation, that means they satisfy our differential equation. So that tells us that all of this is equal to 0, and all of this is equal to 0. Those two things that I've overlined in red. So we have c1 times 0 plus c2 times 0, which is equal to 0. But now reading from here to here, we see that y is also a solution to our differential equation. But the fact that we took any two solutions and showed that the linear combination was also a solution is exactly what it takes for the solution space to be a vector space. So that kind of finishes the proof of this proposition. Okay, let's look at another theorem. Okay, so the following theorem we won't prove, but we will look at a special example. And the following theorem is kind of at the basis of all of our solutions which we'll come up with, or really just showing that all of the solution strategies that we come up work to get all possible solutions. Okay, so let's suppose that P and Q are continuous on an interval AB, and X naught is some number on that interval AB. Then the initial value problem, y double prime plus p of x times y prime plus q of x times y equals 0, with y evaluated at x naught equals a naught and y prime evaluated at x naught is a1, has a unique solution on the interval ab. Good. So let's look at this example. So we've got a differential equation x squared y double prime plus x times y prime minus 4y equals 0. So that isn't quite in this form yet. So let's put it into that form by multiplying by 1 over x squared. That gives me the differential equation y prime plus 1 over x times y prime minus 4 over x squared times y equals 0. Great. So notice that my functions p and q, 1 over x and 4 over x squared, or negative 4 over x squared, are discontinuous at 0. So that means I get unique solutions on the interval minus infinity to 0 or infinity to 0. So let's write that here. So we get unique solutions on the interval 0 to infinity if x naught is bigger than 0, so if it's on that interval, and we'll have a unique solution on the interval minus infinity to 0 if x naught is less than 0, because that puts our initial value in that interval, so less than 0. Okay, so the next thing that we'll do is check that we have a general solution given by the following function. So our general solution indeed can be written as follows. We have y equals c1 times x squared plus c2 over x squared. And I'd like to point out that we don't have a solution strategy just yet for second order linear differential equations. And so we'll just have to take this as a solution, as is. We will check that it's a solution. Okay, so if that is y, then that tells us y prime is equal to 2 times c1 times x, and then let's see, minus 2 times c2 over x cubed. So that's by taking the derivative. And then y double prime is equal to 2 times c1 minus 6 times c2 over x to the 4th. Okay, great. But now if we plug this value of y and this value of y double prime into either of these differential equations, we see that this is indeed satisfied. So I'll let you guys check that. So check this, I'll just say works. So just to reiterate, what we need to do is we plug y, y prime, y double prime into either this differential equation or this differential equation and show that the differential equation is satisfied. So in other words, show that the combination gives us 0 indeed. Okay, so now we have that this is a general solution. Now let's find a specific solution given some initial conditions. Okay, so we just checked that a general solution of y equals c1 x squared plus c2 over x squared solves the following second order linear differential equation. Now we're going to find a specific solution given the following two sets of initial conditions. Now let's notice our initial value of x here is x equals 1, which is larger than 0. So that tells us the interval of validity here will be 0 to infinity. Because that's the interval that 1 lies in, that is also a place where the p of x and the q of x functions, which are not on the board anymore, they're divisions of this and this by x squared, they're continuous. Okay, and then likewise over there, we've got an initial condition where our initial x value is -1, which means our interval of validity over here will be minus infinity to 0. Okay, so that's good. So now how can we find our solutions? Well, we can use these two things right here to narrow down our C1 and C2 by creating a system of equations. So let's maybe recall that y prime, well, let's maybe sneak y prime up here. So that's going to be 2c1x minus 2 over c2x cubed. Okay, so let's maybe box that in blue. So now we have y and we have y prime. So let's see. So y evaluated at 1 equals 2 tells us that c1 plus c2 equals 2. Okay, so just to reiterate, that's this equation right here tells us this equation involving the coefficients. That's just from plugging x equals 1 into this yellow boxed equation. Okay, furthermore, y prime evaluated at 1, giving us 1, gives us another equation. And that equation is something like this. 2c1 minus 2c2 equals 1. So that's from plugging in up here. So like I said, we've got a nice system of equations. Maybe what I would like to do is multiply the second equation by 2. So multiplying the second equation by 2 will give us 2c1 plus 2c2 equals 4. And now we can add these two equations and the c2 term will cancel. So that gives me 4c1 equals 5, which tells me that c1 equals 5 over 4. Okay, nice. And then from there, I can plug that into either of these, and we'll get that C2 is equal to 3 over 4. Notice that 5 over 4 plus 3 over 4 is 8 over 4, which is 2, so this equation is satisfied. Which means my solution here is 5 over 4x squared, and then plus 3 over 4x squared. So that would be my solution here, and that is a unique solution based off of the theorem that we had before. Okay, so now we can do the same kind of thing over here. So plugging -1 into our function will give us something like c1 plus c2 equals 3. Notice the negative canceled out because we've got squares. And then plugging -1 into the derivative, let's see. That gives us something like -2c1 plus 2c3 equals 0. Plus 2c2, I should say, equals 0. But notice that immediately tells us c1 is equal to c2 is equal to 3 over 2. We see that c1 is equal to c2 from this. And then since they add to 3, they both have to be half of 3, or 3 over 2, which tells us in this case, our general solution is 3 over 2x squared plus 3 over 2x squared. Okay, so let's move on and look at some other definitions. So let's look at the following definition. we say that the set y1, y2 is a fundamental set of solutions to our second order linear homogeneous differential equation if every other solution to this equation can be written as a linear combination of y1 and y2. And I should say that this is not a standard definition. At times, there's another characteristic or another rule that y1 and y2 must satisfy in order to be called a fundamental set of solutions. So if you're in my class, this is the definition that we'll use. But if you're learning this on your own or if you're taking another class, make sure to figure out what definition you're using in your class. Okay, and then there's a theorem that says that y1, y2 is a fundamental set of solutions if and only if it is a linearly independent set on A, B. So we won't prove that theorem, but we will use it from time to time. But that really brings up the following question. How do we test for linear independence of functions? So let's recall what it means for functions to be linearly independent, or really vectors to be linearly independent. And there are function vector spaces. Okay, so let's suppose that the set y1, y2 is a linearly independent set. Okay, so what does that mean? So that tells us that if we have the equation c1y1 plus c2y2 equals 0, then the only possibilities for c1 and c2 are 0 and 0. So that's just straight up from the definition of linear independence for vectors, keeping in mind that we've got a function vector space here. Okay, but now let's take this equation right here and let's differentiate it. So that's going to give us the equation c1y1 prime plus c2y2 prime equals 0. That's because the derivative is a linear operator and c1 and c2 are constants. Okay, but now we've got a system of equations. We can write this system of two equations as a matrix equation in the following way. So this is going to be a matrix made up of y1, y2, y1 prime, y2 prime, colliding into the vector c1 and c2 and giving us the 0 vector. So this linear independence condition here is the same condition on this matrix equation that this equation holding implies that c1, c2 is in fact the 0 vector. But this equation holding, meaning c1, c2 is the 0 vector, means the null space of this matrix is just the trivial null space. But that means this matrix is invertible, but that means the determinant of this matrix is non-zero. So the determinant of y1, y2, y1 prime, y2 prime is not 0. But let's recall that the determinant is like the product of the diagonals, the product of the off diagonals, and then you take the difference. So that means that y1, y2 prime minus y1 prime, y2 is not equal to 0. So whether you want to think about it in this blue boxed version, kind of the non-matrix version, or this orange boxed version, the matrix version, that's a nice test for linear independence of functions. But the fact that we've got this kind of nicely constructed matrix here motivates our next definition. We just finished motivating the following definition, which I've expanded to n functions instead of just 2 functions. So let's say we've got functions y1, y2, y3 up to yn. Then their Wronskian is defined by w of x. Notice those are all functions of x. So we're creating a new function of x, and that is the determinant of the following square matrix. In the first row, we have just the functions, in other words, the 0th derivative. In the second row, we have the first derivative. And then in the third row, we'll have the second derivative, all the way down to the nth row, where we have the n minus first derivative of all of those functions. So again, that's just an expansion of what we saw on the previous board with 2 functions. Now we have the following really important theorem. And that allows us to calculate the Wronskian without actually knowing the solutions to the differential equation. So let's suppose that P and Q are continuous on A, B, and y1 and y2 are solutions to the differential equation y double prime plus p of xy prime plus q of xy equals 0. Then we pick an arbitrary, and it's really important that we're picking an arbitrary x naught in AB. Then we've got the following formula for the Wronskian, and this is Abel's formula for the Wronskian. So w of x equals w evaluated at x naught, and then the exponential of minus the antiderivative of our function p. So the Wronskian indeed only depends on this function, which is the coefficient of y prime. And now let's notice that since x naught is arbitrary, we could pick it to be a place where w is 0 if possible, but that means that w of x would be 0 for all values of x, just given it's a multiple of this single value of w. And that gives us the following kind of additional result. And that is w of x is either never 0 on the interval AB, or it's always 0 on the interval AB. So that's pretty interesting. Okay, let's get into the proof. So we'll take w to be the determinant of the matrix y1, y2, y1 prime, y2 prime, which that will be y1, y2 prime minus y1 prime, y2. And now we're going to take the derivative of w. So the derivative of w using the product rule over here on the right hand side will be y1 prime, y2 prime plus y1, y2 double prime minus y1 prime, y2 prime minus y1 double prime, y2. Okay, nice. But now notice we get some cancellation. This term right here cancels out with this one over here. We've got first derivatives of both functions, and then we're left with this object y1, y2 double prime minus y1 double prime, y2. But let's notice that y1 and y2 are solutions to our differential equation. So that means we can solve for y double prime in terms of y prime and y. So let's do that. So now we have y1, and then this will be minus p of x times y2 prime minus q of x times y2. So just to be very clear here, that's what we get if we expand out this y2 double prime, keeping in mind that y2 satisfies this differential equation. So we essentially solved for the y2 double prime using that differential equation. Now we'll do the same thing over here. So this is going to be minus y2, I'll factor that out. And then we have minus p of x, y1 prime minus q of x, y1. Okay, good. Then let's show that expansion as well. So that would be this thing expanding to both of those. Now we get cancellation again. We have y1 minus q of x, y2, negative y2 minus q of x, y1. So this and this cancel. So that's pretty good. And now let's see what we're left with. We can factor a negative p of x out of what's left, and then we'll be left with negative p of x times y1, y2 prime minus y1 prime, y2. But that's exactly the Wronskian, so we get negative p of x times w. But looking at the extreme left and right hand side, we have just created a first order differential equation for the Wronskian. So let's bring that up here and we'll solve that differential equation. Okay, so we just showed that the Wronskian satisfied the following differential equation. Notice this is a separable differential equation. We can write this as dw over w equals minus p of x dx. And now let's integrate both sides with respect to x. But on the left-hand side, we'll have the integral from x naught up to x of dw over w. And then on the right-hand side, we'll have minus the integral from x up to x naught of p of t dt. So let's notice this integral right here is showing up. So that's good. So now let's take the integral of the left-hand side. That'll give us something like the natural log of w minus the natural log of w evaluated at x naught equals minus the integral from x naught up to x of p of t dt. I just fixed that typo a little bit. So now we can move the minus natural log over. That gives me something like the natural log of w of x equals the natural log of w evaluated at x naught minus the integral from x naught up to x of p of t dt. And then from here, we simply exponentiate both sides. So exponentiating the left will give us w of x. Then exponentiating the right and then applying some logarithm and exponent rules will give us exactly what we want. So we've got w evaluated at x naught and then x of minus the integral from x naught up to x of p of t dt. Great. So let's see this formula in action. So now let's look at an example. So let's recall our differential equation y double prime plus 1 over x y prime minus 4 over x squared y equals 0. We had two solutions. y1 equals x squared and y2 equals 1 over x squared. So this is the example that we previously looked at. So now let's verify the Wronskian formula that we had on the last board. So what I mean by verify is we'll calculate the Wronskian two ways, using the definition, given that we have these two solutions over here, and with that Abel's formula, which we had from the previous theorem. Okay, so let's use the definition first. So that means w of x will be equal to the determinant of y1, y2, y1 prime, y2 prime. So that's going to be the determinant of x squared, 1 over x squared, and then here we have 2x, and then minus 2 over x cubed. Okay, nice. So taking the determinant, we have x squared times negative 2 over x cubed. So that's going to give us negative 2 over x. And then it's going to be minus another 2 over x. So in the end, that gives us minus 4 over x. Okay, so that's the Wronskian from the definition. And now let's do the Wronskian from Abel's formula. So that means we're going to have the Wronskian equals w evaluated at x naught, which notice that's a constant. So really this is just up to multiplication by a constant. Maybe I'll change that constant to the number a. And then we have the exponential of minus the antiderivative of, let's see, the function in front of y prime. So I won't be super fancy like we were before with the formal antiderivative. I'll just write 1 over x dx. Great. So let's notice that this gives us a, and then we have the exponential of minus the natural log of x. But then we can bring that minus sign inside, and that gives us a, and then the exponential of the natural log of x to the minus 1. But the exponential and the natural log cancel each other, and that gives us a over x. But we can take a to be anything we want, given that the Wronskian is not unique. It's unique up to multiplication by a constant, unless of course it's always 0. So we can set a equal to negative 4, and we get negative 4 over x, which it matches with what we have from the definition. Okay, so let's end with a little bit of a summary, and then I'll give you guys some warm-up problems. So here's a summary theorem for what we covered today. So we didn't prove everything, but this is the takeaway, I would say. So let's suppose that p and q are continuous functions on the interval a, b, and y1, y2 are solutions to this differential equation, y double prime plus p of x, y prime plus q of x times y on that interval. Then the following 4 statements are equivalent. So that's what TFAE means. The following are equivalent. So the set y1, y2 is a fundamental solution set. So in other words, it spans the solution space. The set y1, y2 is linearly independent. So since it spans and it's linearly independent, it forms a basis for the solution space. So that's kind of nice. That also means that we know that the solution space is 2-dimensional. Then the third thing is that w of x, the Wronskian, is non-zero for some x in AB. And the fourth is that w of x is non-zero for all x in AB. Remember that followed from that theorem that we went over. So you can't just willy-nilly change for some to for all, but in this very, very special case, these two are equivalent. Okay, so let's look at our warm-up exercises. So let's consider the differential equation y double prime minus 2y prime plus 2y equals 0. So just to point out, we'll be able to solve this type of differential equation using a solution strategy in a couple videos. So the first sub-problem here is to show that y1, which is e to the x cosine x, and y2, which is e to the x sine x, are linearly independent solutions of this differential equation on the interval minus infinity to infinity. So we need to first check that they're solutions and then show that they are linearly independent using your strategies for showing things are linearly independent. I would do something like this over here. Then for B, verify Abel's formula. So verify that the Wronskian that you get from these two functions is the same you get from the built-in differential equation. And then the second problem is to find the Wronskian in the two setups. So for these two given functions, y1 is the square root of x and y2 is 1 over the cube root of x. And then for this other case, where your functions are the solutions to the following differential equation, which is known as the Legendre differential equation. So we've got 1 minus x squared times y double prime minus 2x times y prime plus alpha times alpha plus 1 times y equals 0. And that's a good place to stop.